It gives me an enormous pleasure to introduce to you today's speaker, Professor Carlos Stroud. Professor Stroud has been in the faculty of the University of Rochester since 1969. All right. He has contributed to many areas in quantum optics, from the early beginnings of resonance fluorescence, making measurements in theory on resonance fluorescence, all the way through many things. He pioneered beautiful work with Rydberg atoms and so on and so forth. But we were trying to remember when we met first, and it was probably like in 1982. But I would say that whenever I've had a conversation about quantum mechanics with Carlos, it has always been illuminating. And I really am grateful that he accepted on rather short notice the invitation to come. And he said, I had some new ideas that were triggered recently, and he wants to share them with us. Okay, so remember, all the students and postdocs, you are welcome to come to tea at 4 p.m. And cookies on the JQI seminar. The contributions of Carlos are, of course, in science, and the number of students and postdocs that he has produced that are leaders in the area of optics and quantum optics is impressive. We at the JQI have benefited from some of his former students and postdocs, right? So Carlos has really been a very quiet but consistent and persistent leader of the field. Thank you very much for coming.
All right, thank you. This mechanical pointer makes me a little nervous. The last time I remember using one to give a talk, my daughter was in graduate school, and I was asked to give a colloquium in her department while she was a student there. And I was a little concerned. I didn't want to embarrass my daughter. So I gave the talk, and there was a mechanical pointer. And at the end of it, I asked her, how did I do? What did you think? It was pretty good, Dad. But do you realize that you carry your pointer over your shoulder like a rifle? While you're lecturing. I'll try not to do that. The title of this talk, as Luis suggests, is an idea that I just happened to be thinking about that was stimulated on an airplane the day before he called, reading a book. And so it sort of tied together a lot of ideas I've been thinking about for a while. And I want to try it out on you to see whether it really makes a coherent whole or not. I apologize if it doesn't, but maybe there's some ideas here that you'll find stimulating or a little interesting. The idea that was in this book and emphasized that sort of got me to thinking was that nature is analog, but information is digital. Now, this was a statement that an interesting guy, David Deutsch, made in his semi-popular book, Beginning of Infinity. And he was arguing that you can record an analog signal, but when you've recorded that analog signal, you've got something that's still to do anything with. You have to measure it and get it into some numbers somehow. You have to have some kind of ruler to measure what that signal is. You'll still have to do that later, even if you've recorded the analog signal, so that to get information that you can really do anything with, you really have to have it in digital form. And so that was the first sort of thing. The stored analog signal still got to be measured, turned into some finite number of discrete symbols in the end to use them for anything, so to really be information. And furthermore, the digitization error corrects. Automatically you round things off, and so you don't get cumulative error as you try to do further things with it. And so those were extremely important things. And so I started thinking about that in terms of a system that I've worked with a long time, analog signal. this particular one is making wave packets in atoms. So we use a short laser pulse to excite an electron up to a Rydberg orbit. That orbit is about a micron across, maybe a half a micron in diameter. So we've got a big orbit there. And we're actually playing games by measuring the location of the electron around in the orbit. It's wave packets that we're doing there, and the information we're getting out of it is where the wave packet is around in the orbit. So here's a space kind of thing. But we're working with wave packets, so it's semi-discretized in all of this. And so I was thinking about this connection between the discrete and the analog situation when we make these measurements. And of course, there's another thing that we try to measure namely time in the end. And there's another thing that's inherently analog, not digital, and that presents particular problems in quantum mechanics because it's not an operator that we can measure in quantum mechanics. So it again has a peculiar property, but we're often talking about measurements of timing something. Now in the situation with these short laser pulses where we make a wave packet, we can superpose many levels in the atom. We're exciting up to the Rydberg levels so that if we have a pulse that's a picosecond pulse and we tune it up near the continuum, we can excite a coherent superposition of all the levels from n equals 67 to infinity with a picosecond pulse. And so we're forming a coherent superposition, a QDID if you want, a coherent superposition of this whole bunch of levels. If we have a 1 femtosecond pulse in hydrogen, if we tune it up beyond the Lyman alpha here, we can excite all the levels from n equal 2 to infinity coherently, simultaneously with this one pulse. So we can get a QDIT with a lot of levels. That's kind of an interesting system. You think about a wave packet that way and stuff, and whether that is an interesting information system, not thinking about it strictly as a unitary system, but as a coherent superposition with a bunch of quantum levels. Now, in the one example of the kind of information that one might store in an atom is this picture that we made for a funding agency a long time ago, showing here is actually a graph of the wave function of hydrogen, and this is actually n equal 50, and it's a superposition, coherent superposition of the different angular momentum states for n equal 50. There are 2,500 different angular momentum states at n equal 50, and if you make a superposition, here the intensity in the pattern is the probability that the electron is at a given location, and the color is actually the phase of the wave function at that location. So I told the funding agency, look, there aren't many elements to get named after you, and besides, you've got to be dead before they'll name an element after you. But if you fund me, I can write your name on your very own atom. The lifetime of these states is milliseconds, so I'll be happy to make another one. And so it shows you the kind of information that there is can be stored in a given atom. Now, we can't really control the atom. We could, I think, we could do that state. The technology would allow it. Give me a few $1 million in 5 years, I think I could do that. We're there now. But think about this more generally in terms of these wave packets and the information contained in them. We can control the laser pulse that well to determine all of them very easily. But if you think about controlling the wave packet around in the orbit and how well you can control time, we can now make pulses that are 10 to the minus 17 seconds long. That means there are 10 to the 17th slots in 1 second that can be addressed by such laser pulses. That's an enormous amount of information. In fact, the age of the universe is 10 to the plus 17 seconds. So if you simply take the history of the universe with 1 second snapshots, you've got the same capacity as we do in 1 second with these 10 to the minus 17 second laser pulses. So there's a possibility of doing serious things with these atomic systems far beyond a qubit. Now, of course, we all learn in computer science and such that the number of levels, the information you store can only be only goes up as a logarithm of the number of levels. You got a log of the base out in front of that. So it's a losing game. Eventually, you're going to have to, if you're going to build a quantum computer and do serious quantum information, entangle groups of these atoms, these wave packet things, to scale up to large numbers and to efficiently encode information that's in digital form back into them. You're going to have to entangle. And so I was thinking about, okay, we can store information in these atoms like this. Can we entangle them? Can we make a more complicated multi-atom system, multi-Q-trithetic system entangled so that we can scale up? Made these points here. How do we go about making these superpositions? If we're going to make a whole bunch of pulses, not to the 17th of them, but a bunch of them around in the orbit, and we're going to store information with those, how can we do that? Well, one way to do it is with Schrödinger Cat States. You all know what a Schrödinger Cat state is in terms of live cat and dead cat. But a Schrödinger Cat state can be any quantum superposition, coherent superposition of macroscopically distinguishable states. In the case of our Rydberg atoms, we can make a state where we have one wave packet here, the other wave packet here, about a micron across. These experiments have actually been done where it's a millimeter across orbits, and we can put them in a coherent superposition that's a Schrödinger Cat state. It's not a complicated coherent state, it's a superposition of a coherent state, a localized wave packet here, and another one over there. Now those quantum states are essentially a qubit. It's a coherent superposition of these two states, the electron being over here, the electron being over there, and we can have any phase relation between them and any relative amplitude. We essentially have a qubit up there. In fact, we've carried out experiments where we've done better than that. We've made a single wave packet going around in an orbit. We've made two electron wave packets, the same electron, the superposition of being here and there. We've made three wave packets of the one electron spaced out on the orbit like that. And in fact, up to 7 around the orbit have been seen. Now, how do you do that? You can do that by taking the short laser pulse, exciting half, say, of the probability of the electron from the ground state up into a Rydberg state. So you've made a wave packet up there that has half the population of the electron in it. Now you let that wave packet travel around the orbit to the other side of the orbit, and you excite the rest of the population up there. And now you have two wave packets, and if your laser pulses excited them up there are phase coherent, then the de Broglie wave of these two electron wave packets are coherent. So we really have a Schrödinger Cat state. And this is an interesting thing to start thinking about with this quantum information. So let's think a little bit about the mathematics of these things and so on. If To the first approximation, the Rydberg states are almost equally spaced if we have a small range of principal quantum numbers compared to the average one. They're almost equally spaced up there, so they're almost like harmonic oscillators. So you can show, you can define creation and annihilation operators for these things and so on, but they're really very close to a harmonic oscillator. If you're talking about time short compared to the time for these wave packets to disperse, they're harmonic oscillators. So one can treat them and understand their entanglement and so on in terms of harmonic oscillators. It makes arithmetic a little easier. And of course, a wave packet in a harmonic oscillator is a coherent state, which we can expand out in number states like this. And now we can make a Schrödinger cat state like this by having a superposition of one coherent state here on our phase path circle. This is x and p, just the phase space trajectory of the particle going around, oscillating back and forth. And here's the other one over here. And now we can distinguish two kinds of superpositions of cat states like this, the so-called even and odd ones. That is, we can take a superposition of one wave packet here and the other one over here with a plus sign in between, the so-called symmetric Schrödinger cat state, or we can take one where these two have the opposite phase, a minus sign in between. If you think about this, expanding out the coherent state for the one that's alpha here and the one over here 180 degrees away that has minus alpha for its coherent state amplitude, and now we add those together for plus and minus, then the minus ones, all the odd terms are going to cancel out. We'll have the same expansion for this state and this state as far as the even terms are concerned, but the odd ones will have the opposite sign. So all of the odd ones will cancel out, and we'll have a superposition that just involves the even quantum numbers. If we take the odd one, the one with the negative sign here, the even ones will cancel out, and all the odd states will add, and we'll end up with just the odd states. Now these two particular superpositions are clearly orthogonal to each other because this one contains only even states and this one only odd states. Obviously, if I take the inner product of them, it's going to vanish. So this is important that these superpositions like this are orthogonal, because one of the problems with analog signals like this and things like wave packets on two sides of the orbit is coherent states are Gaussians that have long tails and they overlap. And if we're talking about a small magnitude of alpha, the path here is going to shrink. It's the absolute value of alpha is the radius of the circle, and that shrinks down. Eventually these things will overlap, and you won't be able to distinguish the two states in our qubit anymore. But if we take these coherent superpositions, this plus and minus states, those are orthogonal to each other, and so we can make measurements of those and have an orthogonal basis to work with. So we're working with wave packets, but yet we still have an orthogonal basis for these wave packets. Now this is, of course, something that Bloch understands. This is the connection between Monnier and Bloch representations, clear light solid state physics. We can play the same game here. Furthermore, we can generalize it as Bloch did. If we have, instead of 2 wave packets here, say we had 4. And now we can have the phase differences between these as 2 pi over 4, 4 pi over 4, and so on around it. And we can have things that correspond to these, orthogonal sets of these, which are essentially the Bloch waves of these wave packets going around. So we have an orthogonal set that we can have many of these pulses, a Schrödinger cat state generalized to many wave packets, and still have an orthogonal basis to start doing calculations with calculating entanglement, amount of entanglement and so on with it. So we've done that. And now another interesting thing, these Rydberg, describe these things as harmonic oscillators, then we could take and couple one of these harmonic oscillators in a Schrödinger Cat state with another one that was initially just in the ground state of the harmonic oscillator. And if the interaction is a form of A dagger B plus B dagger A, just what we often in quantum optics, quantum information, call a beam splitter interaction, then in fact, if you couple these together with that kind of weakest interaction, lowest level interaction, what you find is that these become entangled. This one's in the ground state, this one's in the Schrödinger Cat state. Then the combined system, after the interaction, will have the first oscillator, if it's in this state, the second one is in the same state. Or if this one was instead in that state, well, then we'll find it's in this one and this one is in that one. And so we get something that looks very much like a Bell state. And in the limit where these don't overlap with each other, it is in fact a Bell state. Yep.
If this were an ordinary harmonic oscillator, then what you're saying would be perfectly clear. But
yes.
This is a harmonic oscillator that you've sort of hooked up by approximating the Rydberg. So what's the ground state? It seems like it's arbitrary which one you take to be.
It's in the whichever is the center level in your superposition. It's in that atomic eigenstate.
Okay, so you just arbitrarily choose some place and say that's the ground state.
That's right. That's right. It's easy enough to set up the algebra just writing A is equal to the sum on ends of the square root of n times the transition operator between adjacent levels, and define all these so you can work out the algebra.
Well, except that for real harmonic oscillators, if you apply the lowering operator to the ground state, you get nothing.
Yeah,
whereas that
right.
isn't going to be true here,
Yeah,
or at least it wouldn't seem to be.
We're exciting it up into an eigenstate. We're exciting from the ground state up into one of the eigenstates up there. And now we're, if you like, hitting it with a terahertz pulse or some such to make the wave packet, to make the superposition of the different Rydberg levels, not the up there.
Sure.
So that's the way you go about it. And it's all a good approximation, so long as you're in a time short compared to the decay time. Which is for time that requires a transfer. Okay, well, we can generalize this further. We could have a generalized Schrödinger Cat state that's in a superposition of 4 levels. And now we can couple that with the same kind of interaction to a set of other oscillators like this that are in eigenstates, and they will end up being superposed into this entangled state, where now we have four of them. Each one of them will be at this location, or all 4 will be in this location, and so on. So this simple interaction can entangle these things quite efficiently, and we can end up with states like these. These are kind of fun things to do calculations with, particularly if you ignore the problems that Bill brought up of how good an approximation this is. But of course, the group down at Rice has done this sort of thing clear up at n equal 1500 or so. So if you get up there, these things really are very good harmonic oscillators. When you get up to that higher level, it's a very long time before these things bring up. Okay. Now we can generalize these coherent superpositions. Our pluses and minuses can be generalized to get these orthogonal sort of block wave state solutions. We've done that even for collections of these that are entangled, And we came up with an operator, sort of like the squeezing operators or the translation operators that generate coherent states. We've defined the general operator that you can operate on a state like this to produce these entangled states in this form. I had great fun doing that because it turned out that this C operator here is actually, there's a special function associated with it, and that special function doesn't seem to be in the literature. And I had enormous fun over a weekend of actually working out all the properties and all the identities for this. It turns out you can work them all out. And these are things that you think about it. What are these? You start out the lowest level is exponentials. The next level has sines and cosines. That's our even and odds in the sums. And then the next one has every third term in expansion, every fourth term in expansion, or the higher order ones, and so on. So you get these peculiar polynomials that are of that form. And so you can work out the properties. I couldn't figure out where you publish your own function, so I did get it into Physical Review in an appendix. That's this paper right here. Now let's think about the dimensionality involved in this system here. One oscillator, of course, has an infinite number of states, and we have a hard time doing entanglement calculations and such with an infinite number of states. But coherent states only have two parameters. They're described by complex alpha here. They're described by two parameters. So by making these things wave packets, we don't see the whole dimensionality of this. We can discretize it in terms of these discrete number of wave packets around the orbit, and that can reduce our parameters down to something that we can handle. And that's one of the points from the original title of this, is that even when you have a spatial coordinate that you're trying to measure, there are ways of discretizing that, not just in your measurement process, but in your basis, physical basis that you're working with, that end up discretizing the problem. And that's what we're doing here. And so if we have m different wave packets around our phase-space trajectory, then we'll have 2m parameters. So the dimensionality of the system is 2m. And now working with these operators and such, we have 2m by 2m, and we can go ahead and work with those. The problem is they aren't orthogonal, but we know how to solve that by going into these block basis forms for those with superposition. And we can calculate what happens. In this particular case, we calculated the entanglement between a pair of group of oscillators. In this particular case, we had 5 wave packets and 5 oscillators coupled together. One was initially excited, and it was symmetrically coupled to all the others. And we watched the time evolution of the entanglement among those oscillators. And here's the time dependence. Here they're completely entangled. That's when the population is equally distributed among all 5 of them, and we can get maximal entanglement. And other times when all the population is initially in just one of the oscillators, or it comes back periodically to that one again, we get the entanglement going down again. It doesn't quite go down because we have finite overlap between these with the excitation level that we're working with. How do we go about calculating entanglement with this system that has 5 particles and 5 states? Well, it turned out that there's a paper that I'll talk about in a moment that defines the kind of purity that will actually work for this system. And that's developed by Camille's group out at Los Alamos. They came up with this technique. I won't go through the details of it. If you want, I can tell you a little bit more about it. But we can actually do the calculations with these systems and work out time-dependent oscillation of the entanglement. And with harmonic oscillators, hey, we can do chains of these, starting excitation here and watch it propagate down the chain. We can have rings of them. We can have one coupled symmetrically with the others. We can take all these problems. This is just coupled harmonic oscillators. So we can do any kind of calculations that we want with these things for their ways that they're coupled together and work out their time dependence and the time dependent entanglement. And so we've done that. It turns out that the maximum entanglement is when there are equal numbers of wave packets around the orbit and numbers of particles. That turns out, that's these graphs we calculated that show that. Now, what about stability of cat states? There have been a series of papers saying Schrödinger cat states will never be useful because they're unstable when they interact with the environment. And so we wanted to check whether that's true, and if so, why they're so unstable. It's not so clear that they're unstable if you look at these Rydberg atom experiments, because we actually see these wave packets go around many, many orbits, and then the wave packets interfere with each other. So we get interference fringes. In fact, we've done the equivalent of Young's double slit interference patterns with these wave packets over long periods of time. So they're remarkably stable. But we can do the calculation with harmonic oscillators, so we try. So what do? We took here N oscillators, that should be sub N here, N oscillators all the same resonance frequency, and we couple it to a bath. Here's the bath oscillators. The bath oscillators, of course, have a range of frequencies, and the coupling constant here, if it's very smooth, so it doesn't vary very rapidly over the bath, then we're in the Markov regime, and we do a calculation which is essentially just doing a Weisskopf-Wigner calculation like we do in spontaneous emission, but we're doing it for this collection of oscillators. So it's straightforward to do that. We're just, again, the bath is described by oscillators, and the medium is described by oscillators, and they're coupled together by our B dagger A kind of interaction. So all the stuff we were doing before works. We can carry out the calculation, work out the probabilities for the system, and so on. And what's going to happen? Well, we've already seen when you couple one oscillator to another, and it's in the Schrödinger cat state, that it produces, that it becomes entangled with it. So what's going to happen when our matter oscillators in a Schrödinger cat state interact with the bath? Well, the oscillators are going to become entangled with the bath oscillators. But the bath oscillators have a range of frequencies. So the bath oscillators will quickly dephase, and that will destroy the entanglement. It'll destroy the coherence of these oscillators, so our Schrödinger cat states will decay away. But it's straightforward to do this calculation here. It's super radiance, really. We've got a collection of oscillators. They're all coupled uniformly to a bath, and we see the decay. And that's with a single atom. That's what Vicky Weisskopf did in his PhD thesis in Victor in 1932. So what are the results? We find that the matter oscillators do become entangled with the bath oscillators. That the bath oscillators rapidly dephase, and that destroys the coherence between the Schrödinger cats. The cat states are no longer phase coherent, but rather an incoherent mixture of the coherent states that destroys the entanglement. Once the coherence is gone between the two sides, then we just have incoherent superpositions, and you can't have entanglement. So the entanglement vanishes. Now, how fast is this decay of the entanglement? What's the time of You can work it out explicitly in this model. And what you find is that the coherences for the individual oscillators decay like this, super exponential. E to the minus 2 alpha squared, that's our coherent state amplitude squared, times a 1 minus e to the minus 2n gamma t. What's this? That's the super radiant decay time. The e to the minus gamma t is how one oscillator would decay interacting with this bath itself. There are n of them coherently radiating coupled to the bath, and so we get the super radiant rate here. But now look what happens. We have this thing is decaying like it normally would, like any state would decay in this situation. But now the decay is amplified by this coherent state amplitude. The bigger we make our orbit, the larger alpha squared is. That's the square of the radius of our orbit in phase space. And so the rate at which this thing decays is going exponentially, getting exponentially more rapid as we make the thing larger. More classical, larger coherent states. So super exponential decay. This is the basic reason that people have argued against coherence, the Schrödinger Cat States as being useful, because their coherence decays away so rapidly because they become entangled with the bath oscillators, and the bath oscillators dephase. So that will kill you. But of course, this is the if there were no decay constant, up here, this thing weren't decaying at all, then this would become a 1. 1 minus 1 is 0, and we wouldn't get any decay. So if there is no decoherence by the single atom or single oscillators, or that is the oscillators that aren't in the Schrödinger Cat States, then this effect won't occur. Well, we've got this maximum decay rate here from the superradiants because we have n of them that were all coupled to the bath exactly symmetrically. And they decay, and we assume that we're excited in that symmetric state. And that decays superradiantly. But there are also subradiant states, or decoherence-free subspaces. If we took two Schrödinger Cat States and we put them in an anti-symmetric superposition with each other, the two different, here's one oscillator in Schrödinger Cat State, here's the other one, but we're in the negative superposition of these two states, then when they interact with the bath, they're decoupled with it because the bath interaction is symmetric and they are anti-symmetric. These are the subradiant states of Dickey, where essentially you have two dipoles that are out of phase, they don't radiate. So that's exactly what would happen here. So there are decoherence-free subspaces in this, which even though the superradiant state will decay away extremely rapidly, the decoherence-free subspaces will not decay. Now, this can actually lead to something rather wild, namely sudden birth of entanglement. That we can have a system that's initially unentangled, we couple that unentangled system to a reservoir, and it becomes entangled. Now, how does that work? Let me show you. Two oscillators, for simple example. Initially, one's in a Schrödinger Cat state, and one is unexcited. We symmetrically couple them to a reservoir. There's no entanglement because one of them is not excited. The other one is in the Schrödinger Cat state, so no entanglement. Now we let them couple, and what's going to happen? What's going to happen is that this one that was initially excited will couple to this one and become entangled. And in fact, the superposition of one that's initially excited and the other one in the ground state is the sum of one cat state plus the other cat state plus one cat state minus the other state. The sum and differences of those will cancel out to give you just one. So the symmetric combination is going to actually decay away rapidly, and you'll be left with the anti-symmetric combination that's entangled, and so the thing becomes entangled.
When you say it becomes entangled, you mean the subset of things that are left after
The sub
the
things,
decay?
the half of them in this particular case will be left.
But unless you select on that, if you started with the whole ensemble, you don't know which are in that remaining state.
If it's a coherent superposition initially, and it's a superposition of all of them that are in this particular state, half of them.
So is it going to be half if you start off with a large ensemble of pairs of oscillators, paired the way you've described? Is it half that end up in the
That's right.
the decoherent street?
Yeah. So, but they would be entangled just pairwise the way you just said. Yes. We could take one and couple it to n other ones, the same kind of way, and now then the thing would lose all but the 1 over n. The population would be lost like this. But if you just had two of them, it would be half that would be in this initial state. Or if you can figure out some way to put them in the decoherence-free subspace in the first place, then of course they would stay there. Well, we actually used this same measure of entanglement, and because we were coupled to a reservoir, of course we had to make a convex roof extension to carry out the entanglement studies, but we did that. That's published in this paper in 2010. And so we actually have the time-dependent entanglement and how it decays. The individual atom decays would be 3 to the minus e to the minus 3 gamma t up here. And here is what the decay of the system would look like in the case of alpha equal to 1, alpha equal to 2, alpha equal to 4, and alpha equal to 8. And so you see this rapid decay, super radiant decay of the super exponential decay going away for large alpha. That's that e to the minus alpha squared. That alpha squared up in the front is what's causing this. As we get to larger alpha, more coherent state, we get more rapid decay of the entanglement, or in the other case, producing the entanglement even more rapidly. Okay, other breeds of cats. This is Rydberg wave packets, and what led me to think about this. Of course, there are other kinds of Schrödinger cats. They produced Schrödinger Cat States of ions in a trap. There have been other Schrödinger Cat States, a little bit controversial, but of photons as well. So nobody's entangled the Rydberg wave packets yet, though of course there's been lots of work on Dr. blockade and so on, Rydberg atoms, interaction between Rydberg states, but not Rydberg Schrödinger Cat States, but it's certainly doable. Photons. Trying to make a Schrödinger Cat state with the photons is non-trivial. There's some groups trying to do that right now. People have done that with alpha less than 1. But these effects aren't very good for alpha less than 1 because the circle is so small that the two wave packets in the cat state overlap each other quite a bit. So it's not too great a basis. So you'd like to do it with larger alpha. There are some groups, I know Jim Franson, for example, is working on trying to make such states with photons. Orbital angular momentum states are kind of interesting states. Obviously, our wave packet states here going around the orbit are described angular momentum states. It could be orbital angular momentum states excuse me, of photons as well. And there are these, they call them coolers or whatever, that take these states and turn them back into discrete states. In that case, that's really the same as these block states that we're talking about here. You can choose the relative phases between either the IM phi, either the m plus 1 phi, and so on, superposition of those states, and make localized wave packets and vice versa. So a lot of this analysis could be carried over to orbital angular momentum states with a single photon. There's some other possibilities, certainly of making these Schrödinger Cat States and other systems. Interesting thing certainly would be trying to carry this over into some wave packets and condensates and such. I think there's some possibilities there that I asked about. Now, the last thing I wanted to bring up was this time question. The ultimate of the continuous variables is time, and it's a peculiar thing in quantum mechanics, of course. That time is a parameter in quantum mechanics instead of an observable. But the interesting question is, can we somehow play games like these with time? Is there something we think of time generally as something that runs on continuously in a straight line. For a free system, it is that way. But of course, at NIST, we make atomic clocks and such by using periodicities in time, so that there's a definite period that's quantized. And how do those things come up? It of course comes up by the fact that there's energy is quantized in atomic systems, and we have the Einstein relation between energy and frequency, and then that turns into a time simply like this. This is a little more complicated, as you all know, better than I do with the clocks. But the basic idea is still this, that we get a cyclic time because we're talking about quantized energy levels. The quantized energy levels have transitions that beat periodically in time. And we can take advantage of that and essentially quantize in time by the time it takes the electron to go around the board. It's quantized that way. So there is a way, there is quantization of time in a sense. There's another way, which is rather fun to think about. Can we actually have time as an operator with eigenvalues? Well, it turns out you can, in a particular problem that's somewhat related to this one with the atomic clocks. If we excite these Rydberg atoms up to a high excited state, and we let them evolve, they operate just like a harmonic oscillator with non-dispersing wave packets for a while. But the energy levels aren't exactly equally spaced, so the wave packets disperse. After they disperse, they interact with each other coherently, and we get an interesting sort of periodic time dependence of the system. And here's a movie Stroud once every round trip time of the orbit to see what the wave packet looks like over longer times. And you see it builds up this whole series of things. These are called fractional revivals. Here it's the 1/3 fractional revival. We have 3 wave packets going around the orbit. A little later here we have, or at the 2/5, we have 5 of them. Now 2 of them and something. So these revivals and fractional revivals of the wave packet are just the fact that we've excited a bunch of different atomic levels. We've excited a bunch of them. And now our wave packet is the beat between these different energy levels that are excited. We're getting beats between those. The energy levels aren't quite evenly spaced. And because they're not quite equally spaced, this beating does peculiar things. If there's a finite, if we had the levels were spaced out like in a square well, then the energy levels go like n squared. And so n squared is an integer of n's an integer, so it's periodic. If we put that in exponentials, that's a Fourier series, it's periodic. But in the case of Rydberg atom, it's the energy levels go like 1 over n squared. So they're not spaced with integer spacing. So the beat pattern is complicated, and it depends on how many levels are there when they come back in phase with each other to give a big single wave packet, or they give these other revivals here. There's eventually a Poincare recurrence time over long periods of time when they come back, but they come back almost perfectly at shorter times. And so these are things that's kept us busy for 25 years in the Rydberg state wave packet stuff, studying all the properties of these decays and revivals, manipulating these. So they're well studied. But this gives us a different kind of times that come up. Here's a series of times. That's when will this thing have a full revival? When will it have a 1/2 fractional revival or 1/3? Predicting that for these systems can be rather complicated if you're talking about the 10th revival. And in these things we actually have decays and revivals of the decays and revivals, and then a hierarchy like that. So predicting when these things are actually going to occur is difficult. Well, we set that up as an eigenvalue problem. You can actually make it an eigenvalue problem. And so we've got a quantity that we're calculating, which is the time of these revivals, and it becomes an eigenvalue problem. This student of mine and I published David Ehrenstein. And let me go through quickly the basic idea. I think it might be useful to some of the problems that I talked to some people around here already this morning. So the wave function for our atom looks like this. So we have the wave functions here, and then the time dependence are simple exponentials at the Bohr frequencies omega n of the individual levels. And the decays and revivals are just beat between these things at the different frequencies there. Well, we can take those frequencies here and we can expand them out in a Taylor series in n. They're not quite equally spaced. If they were exactly equally spaced, then the expansion in n would only have a constant term plus the linear term, n. But because they're not spaced like that, we'll have n squared, n cubed, and so on terms. So what we have in the exponential is something that's the exponential times a polynomial in n, where we've cut it off at some capital N here. There's n levels, capital N levels in the superposition, so we can have a polynomial up to that level. And so we're trying to find not what this polynomial is, what the frequencies are, but the times for these revivals. And the way we did that was we wrote it as an eigenvalue problem. It's a discrete difference eigenvalue problem, and it's of this form, that the n plus first difference as a function of n of the frequency times the time is equal to a multiple of 2 pi. Simple enough, and what I mean by those finite differences there is that if you have a function here with a parameter n, the first difference would just be the difference between this function here at n plus 1 minus n. The nth difference would just be the second difference would be the difference between two pairs of these, and so on. The nth one looks like this. So there's what our operator is here, and we solve this, and that turns out numerically to be very easy to do. For a more or less arbitrary system, it's easy to do that, and you can work out very accurately what all these decays and flattens. So we're not quite finding eigenvalues of observable here in the quantum mechanical sense, but we really are solving an eigenvalue problem that finds discrete times, and it comes about because because the levels are discretized in the first place. We have discretization; these omega n's are discrete from the quantization of energy, and that gets turned into the discretizing of the times of the remodelings. So it's a rather interesting thing. It's even interesting thinking in terms of time, setting time standards and such, because it essentially is a vernier of the usual kind of atomic clock. Now, instead of having 2 levels involved, and we're measuring the frequency there, it's 3 levels, and we're measuring the difference frequency on those things, or 4 levels and so on. So we can have more levels multiplying together and taking the way the frequencies vary, transition frequencies vary over all of those to determine this time interval. So it's kind of an interesting, whether that could lead to greater precision, I don't know. It's an interesting thought. So takeaway points. Even continuous variables such as coordinates and time can be naturally discretized in bound quantum systems. We have bound quantum systems like our Rydberg atoms or our these other systems that I've mentioned. We can have natural ways of discretizing in terms of these Schrödinger Cat States, these essentially states where we have wave packets around some closed orbit. It's a bound state, so we get closed orbits. The generalized Schrödinger Cat States can form qubits that can be entangled, forming interesting systems for quantum information. Whether it's for practical application of quantum information or just a different way of thinking about these problems, I think it's an interesting system in quantum information. The time-dependent entanglement of these things can be calculated using this form of purity. It turns out to be very nice because we don't have the general kind of n-level system here. The entanglement is a very special kind with these symmetric wave packets around the orbit. So there's a well-defined measure of the entanglement in these systems. Decoherence can produce as well as destroying the entanglement in super short times. The time evolution of these is very fast in any coupling to reservoir. They're extremely sensitive to the reservoir couplings. And that usually hurts you, but if you're clever about it, it can actually help. And basically, that again, that it's the entanglement with the bath that's causing this rapid dephasing. So that concludes it. I hope we found some ideas worthwhile.